In the first part on flying physics, we saw about the level flight and the climb, but what goes up must come down and turn around. That's so stupid. Hi, I'm Grant and welcome to class 15 in the Principles of Flight series. Today we're going to be looking at the second part of our flying physics, and we're going to be covering the descent as well as gliding and also turns. As we did with the climb, we have to first look at some definitions between flight path angle and pitch. It's slightly different to the situation with climb. As we see here, our pitch is our angle between the horizon and the longitudinal axis, which is no different from before. But in this case, we add on our angle of attack to find out our descent angle. In the situation with a climb, it was the reverse. You would add on the alpha and the flight path angle to get our pitch. But in descent, because we're going down and the angles are different, our total angle is our flight path angle plus, our flight path angle is our pitch plus our angle of attack. When descending, the steepness of the descent will influence how much of the weight is acting into the slope as well as acting down the slope. Same thing as we saw in the climb situation. The difference this time is that the weight is actually added onto the thrust. If we look at the diagram here, we can see that the value for the force that needs to be added to the thrust is W, the weight, times sine of the flight path angle, sine gamma. That's the proportion that's acting down the slope. So that means the drag for a steady descent has to be equal to the thrust plus W sine gamma. And that also means that the proportion acting into the slope must be balanced out by the lift. So we get L, the lift, equals weight times cosine gamma. This means that in the descent, the weight is greater than the lift because you're only balancing the lift out with a proportion of the weight. It also means that the drag is greater than the thrust. You've got a bit of thrust here that is balanced out by the drag, but the drag also has to be large enough to account for the proportion of the weight here. So the angle of descent isn't dictated by how much power we have available as it is for a climb, because we don't need to fight any weight. We don't have to use thrust to fight any weight. We actually just use the thrust to fight the drag. So if we do a bit of rearranging of this bottom formula here, we can see that sine gamma is equal to drag minus thrust over weight. So the factors that influence the steepness or the largeness of this sine gamma factor are having more drag and less thrust. So when we're doing a steady descent, we can do that with power or without power. Without power is when we're gliding. Our equilibrium state when we're gliding slightly changes when we're in the descent. We still have the lift equal to W cosine gamma, that amount of force that's acting into the slope. But when we're acting down the slope, we take away this thrust that was off the front here. So we now have drag equal to W sine gamma. Because there is no thrust to help oppose the drag, that means that our angle, our sine gamma, has to be much steeper to mean that we've got a large proportion of the weight to account for this drag. That's why you have to descend at a steeper angle, and that means that you can't fly as far, which is why gliding is a lot worse than descending with power. So again, you can rearrange this just to find out that that is true. Sine gamma equals drag over the weight. So basically we have to reduce our drag as much as possible to allow us to get the smallest value for sine gamma, which will allow us to travel the furthest. The speed where we have the least amount of drag is VMD, that bottom of the total drag curve that we've seen a few times now. That speed is also the speed where we get our best lift to drag ratio, which makes sense. To fly further, we must optimize lift and reduce the amount of drag that's pulling us back. Sometimes it's not all about getting as far as possible when gliding though. Sometimes it's all about how long it'll take for us to glide down to the ground. Because if we maximize the length of time we're in the air, we have more time to try and restart an engine, for instance. This basically means that we've got to change vertically at the slowest rate. We've got to minimize our rate of descent. And what you're looking at when you're looking at minimizing your rate of descent is you're essentially trying to look at energy conversion from potential energy, height energy, into this kinetic energy over time. That's why you get the rate. And the rate of converting one energy form to the other is known as power. So you're looking to expend the least amount of power. This speed that this occurs is known as VMP, minimum power used, and that occurs at 0.76 VMD. It's slower than our minimum drag speed. So there are a few factors that affect the glide and the steepness of the angle, and also the endurance. So weight has no influence over the glide angle, which does seem a bit strange because it's involved here. The reason for this is that when our weight goes up, our lift has to go up to balance it as well. And if our lift goes up, that means that our induced drag also increases. So that means that our lift goes up, our drag goes up, and our weight goes up. This means the lift to drag ratio, both going up by the same amount, so that remains exactly the same. And that means that the same distance can be covered because we've got exactly the same lift drag ratio. The only difference is that because we have now more induced drag, our total drag curve will move up and to the right, something like this. That means that our VMD now occurs at a faster speed, so the heavy aircraft will have to fly faster along the ground, which means that the endurance, the length of time that we're actually in the air, will reduce. So weight has no effect to angle, but a heavier aircraft will have reduced endurance in the glide. So by extending our flaps or our landing gear, we increase the drag significantly, which means that our value for sine gamma goes up, and that means that we have a steeper angle. So this is no flaps, and this is flaps down here. As you can see, a much steeper angle because the drag goes up a huge amount. So the steeper path also means that we're going to land earlier, so our endurance reduces. Flaps or gear, bigger angle of descent and also reduced endurance. The effects of wind can either help or hinder us in the glide. With a tailwind, we get an increase to our horizontal speed over the ground, which means our range is increased. We get pushed along the ground a lot more, and that essentially means that our descent angle is shallower. The headwind does the opposite, and it will stop us from traveling in the direction we want to. It will push us back along, and that means that we travel a shorter distance horizontally, and that essentially means that our flight path angle, our descent angle, is a lot steeper. Both of these winds, either a headwind or a tailwind, have no effect on the rate of descent. Because they are purely horizontal winds, it means that they have no vertical component that will affect the rate of descent. It's only the horizontal that is affected. The vertical isn't getting blown by the wind at all. So that conversion of height potential energy to kinetic energy still occurs at the same rate. There's nothing that's pushing against us or nothing that's pushing behind us to help us down. So tailwind will extend the range but have no effect on endurance, and headwind will reduce the range but also still have no effect on the endurance. Turning occurs due to a centripetal force, not centrifugal. Centrifugal is out the way, centripetal is in the way. And this centripetal force moves us in towards the center of the turn. It pulls us in towards the turn. That's what allows us to turn in the first place. The stronger the centripetal force, the more severe the radius. The shorter the radius and the more severe the turn. So you've got a weak force here that only forces you to turn a little bit, and then a very large force here that will turn us around the corner a lot more severely. In aircraft, we generate this centripetal force by using a component of the lift force, and this is achieved by rolling the aircraft using the ailerons or banking the aircraft. When we bank the aircraft, not all of our lift force is now opposing the weight. It's only a portion of the lift force. It's only this cosine theta element, this straight up element. That means that if we don't do anything to increase the force, that our weight will be larger than this component. So what we do is we actually have to increase the total amount of lift so that this vertical component remains sufficient to fight the weight. We do this primarily by increasing the angle of attack and pulling back on the controls to slightly raise the nose in the turn. This increase in lift means that our lift to weight load factor goes up and we start to feel heavier as a result. That's why you get that feeling of heaviness in a turn. This increase in lift will also increase our induced drag, which will need to be balanced out by thrust if we want to maintain a steady turn. The size of this bank angle determines how much of our lift is used for turning to generate that centripetal force and how much is used to oppose the weight. If we look at the diagram, we see that the upward component of our new lift force must equal the weight for us to be balanced. That means that we can say W equals L cosine theta, weight is equal to lift cosine theta, and we can rearrange that so that cosine theta is equal to weight over lift. And by rearranging, we can substitute in the load factor. So 1 over cosine theta is equal to lift over weight, and that is the load factor. The centripetal force, this element here, can be calculated using the tangent. So it seems a bit counterintuitive why we're not just using the sine, but it does make sense later on. So the tangent of the angle is equal to the opposite over the adjacent. So the opposite in this case is the centripetal force that we're looking at, and the adjacent in this case we know has to be L cosine theta, or it's the weight. It has to equal the weight for us to be balanced. So we're going to substitute in the weight there, and then we can take this a step further by using the formula for centripetal force. We can say that tan theta is equal to the centripetal force formula, which is in here, mv squared over r, and that's also divided by the weight. And then again, we can say that the weight is equal to basically the mass times the acceleration due to gravity. So we substitute that in. Tan theta equals mv squared over rgm. The two masses on the top cancel out, and we have eventually, after a bit of maths wizardry, tan theta equals v squared over rg. So why have I done all that? That is basically to show that the mass has no effect on the radius of the turn. An aircraft that travels at this speed and at this bank angle will have exactly the same turn radius no matter the size of the aircraft, no matter the weight of the aircraft. It's all about the bank angle and how fast you travel into the turn. So when looking at climbing and descending turns, the outer wing of the aircraft has to move faster through the air because it has to travel further distances. This means that it generates more lift and also helps with that turn. Another thing that happens, depending on whether we're climbing and descending, is the relative airflow comes in at different angles. So if you think about the normal angle of the relative airflow coming in at this sort of angle here, but then when we're climbing, this outer wing is going to be moving away from the airflow. It's going to be rising up against the airflow. So that means that the overall angle that the air comes in at is a lot steeper, and you get a larger angle of attack as a result, because the air is coming in forward like this, and the wing is moving away from it, so it starts to hit at a steeper angle. So because of this faster moving wing as well as this larger angle of attack, you get the tendency to overbank when you're in a climbing turn. That outer wing is very happy to turn, and it turns the aircraft over. It forces it to roll more. And then in descents, it's the opposite case. You have the outer wing with more lift and the inner wing with less lift, obviously. And then when you're in a descent, you're moving towards the airflow. Your air is coming in like this and you're kind of moving down to meet it. which means that your angle of attack actually reduces. What that means in practice is it's the opposite case. Because of this reduced angle of attack, you get an underbank when in a descending turn. It's more likely to not want to turn. So the concept of coordinated turns are when the angle of bank, the speed and the load factor are all in sync and all harmonized. We do this by using the rudder on the tail of the aircraft. Basically, if we don't balance out the three factors well, we will either have the feeling of getting heavier and pushing us out of the turn, and it will not be balanced by the centripetal force pulling us in, or we will generate too much centripetal force and we will fall into the turn. By using the rudder, we can add in additional turning forces to stop the skid out of the turn and adjust the bank angle to allow us not to slip into the turn. Skidding and slipping may not seem that important, but if the turn is out of balance, it feels really weird. Your stomach is all over on the left, you're turning as much as you should, your eyes are telling you you're not turning at all. It's just a recipe for vomit. It makes you feel really weird when you're not doing a coordinated turn. So to assist with this, we use an instrument called the turn coordinator. It's a very crude drawing. You basically have an aircraft and a tube with a ball in it and a couple of bank line indicators. The ball in the tube essentially shows you your centripetal force, and if it isn't in the middle, then you are not in a coordinated turn. To correct this, you step on the ball. So if it's out to the left, you put in left rudder, you extend your left foot, and if it's off to the right, you put in some more right rudder. That means that you'll then coordinate the rudder with the turn as well, and you won't get this feeling of an uncoordinated turn that makes you feel very sick. These indicators here are what we use for something known as a rate 1 turn. So this doesn't show any actual bank angle, it just shows you a rate of turn, which is equal to 3 degrees per second. This is used a lot by ATC as a delaying function. They'll tell you to orbit left, for instance, and what they mean is make a turn of 3 degrees per second to the left, which essentially equates to a 2-minute 360-degree turn. You also get rate 2 turns and rate 3 turns, but they're not as common, and basically they equate to 6 and 9 degrees per second. So to summarize the flight physics for turning and descending then, our flight path angle is slightly different in the descent than it is in the climb. It is actually equal to our pitch plus our angle of attack, whereas in the climb, the flight path angle plus the angle of attack equals our pitch. When descending, different proportions of the weight either act with the thrust or oppose the lift. So that means that our formulas for a stable descent are as so. The drag is equal to the thrust plus W sine gamma, and the lift is equal to the weight times the cosine of gamma. What that means in essence is that the drag has to be larger than the thrust because it has to overcome the thrust plus this proportion of weight, and the lift has to be smaller than the weight. Lift is less than the weight because the lift is only a proportion of the weight here. If we do all these rearrangements and stuff, we can find out that the angle for our descent is dependent on the drag and the thrust. We want to have as much drag as possible and as least thrust. In a glide, we have no thrust, so our descent equation equals drag equal to W sine gamma, and the lift is still equal to W cosine gamma. Because we have no thrust, that means that we have to descend at a steeper angle to balance out this drag, and that is the reason why we can't fly as far when we're gliding. If you rearrange, you can see that sine gamma is equal to drag over weight, and essentially you want to then reduce your drag as much as possible. That means that our best angle of descent, which is essentially the lowest angle of descent that will allow us to fly the furthest, occurs at the spot where we have the least drag, which is this VMD. Best endurance, on the other hand, is dependent on that rate of change between height and, potential energy to kinetic energy, and the rate of change of energy is known as power. So we have to get a speed which is minimum power, VMP, and that occurs at 0.76 VMD. In terms of the effects on these angles in the glide, the weight makes no difference at all, except it means that we've got to fly at higher VMD, and that means that our endurance decreases because we've got to fly faster. Flaps increase the drag and therefore make us descend at a steeper angle, and that steeper angle means we hit the ground sooner, and that means that our endurance is also reduced. And in terms of wind, a tailwind will increase the range, a headwind will reduce the range, but neither of them have an effect on that rate of descent because it's no component either up or down, it's just a purely horizontal component that's added through that wind. So in a turn, we use some of the lift as a centripetal force that allows us to actually turn around the corner. That means that the weight must be equal to lift times the cosine of this bank angle, and we need to therefore produce a larger amount of lift to have the weight and the lift cosine bank angle in balance. The way we do this is we pull back to increase our angle of attack, which means that our overall lift force increases, and that means that we feel heavier when we're turning. The weight is equal to lift cosine of the bank angle, which when we rearrange, we get 1 over the cosine of the bank angle equal to the load factor tan theta. We're using tan because we know that this force, L cos theta, has to be equal to the weight. So we then substitute in, it's the central force, the opposite, over the adjacent, which is the weight. And then when we substitute in stuff for weight and the centripetal force formula, we essentially boil down to v squared over acceleration due to gravity is the rate times the radius of the turn. And that shows that the weight has no effect, the mass has no effect on the turn. It's only the speed that affects the radius of the turn as well as the bank angle. In a climbing turn, we have an increased angle of attack on the outer wing, which leads to an overbank situation. And in descent, we have the opposite, which leads to an underbanking situation. Turn coordination that we use to avoid that feeling of making us sick in uncoordinated turns is done through the use of a turn coordinator, and we step on the ball to correct. If the ball is out to the left, we step on the left, and if it's out to the right, we step on the right. And the other element of the turn coordinator is this little aircraft symbol with the tick marks, and those tick marks will indicate rate 1 turn, which is 3 degrees per second. You also get a rate 2, which is 6 degrees per second, and a rate 3 turn, which is 9 degrees per second.